My name is Paresh Gupta. I'm a technical marketing engineer in Cisco. I'm also an author of a book on detecting, troubleshooting, and preventing congestion in storage networks. There's an entire dedicated chapter in this book focused on RDMA storage network. If you replace storage in that chapter with AI/ML, everything applies to this conversation today. I'll be joined in a few minutes with Nicholas, who is a machine learning engineer at Cisco, and he'll share his experience of building a generative AI application using the infrastructure that I operate. And today, in addition to all of you, I also want to address the network engineer community. There's a large community of these network engineers across the entire world that who operate the networks in enterprises. And how the combo between me and Nicholas would really align with them, because they would be running a same environment on-prem and helping to create a generative AI application based on the on-prem data, which cannot really leave the premises, right? It's very similar to Cisco's environment that we have a lot of private data that, I can access because I've gone through the trainings, but we cannot put it on the cloud for training, right? So it's the same journey that I believe that most of the enterprises will go through. Now, when we talk about, in addition to what Jake talked about, the solution approach from Cisco, what we are doing, we are qualifying many GPU vendors, of course, the leading ones, which is AMD, Intel, and NVIDIA, and providing those validated solutions to our customers. This also includes the storage vendors. So what you see here on screen, this is the environment that I operate. This is based on a 256 GPU cluster based on Intel Gaudi 2. If you look at the photo, it looks very uninteresting. You see most of the rack is vacant. The reason for that is because these servers consume so much power that we cannot do more than one server per rack. And by the way, in all honesty, I'm not sure how many enterprises are ready to go to those next generation data centers, which can provide like more than 10.
It's like an accordion. You have to literally extend the accordion out.
Yes, at that level. And also, this server is probably 10 or 11K per 8 RU, kilowatt per 8 RU. I think the H200's one, probably, if I'm right, it's 14 kilowatts. So that really dictates what kind of power they are going to consume. And also for network engineers, I like them to think in the direction that what would it do to their cabling, right? That's something I'm going to talk more in a few minutes. But the point that I'm trying to convey is that Cisco is validating most of these solutions. And we are offering not just a validated design configuration, as well as the automation that we have built around. So you see some of the screenshots. It includes the day two ops. And by the way, one of my own learnings is that at least I don't like to call this as day two ops anymore, because with GPU cluster, with this 256 GPU cluster, it's operating like a single computer, if I can really simplify it to that level. And if anything goes wrong in one of these components, the entire training job stops. And then Nicholas would come to me and say, like, Paresh, what happened? What did you do? It's like, I don't know. So I need that visibility on day one. Otherwise, I cannot operationalize this environment. Now, imagine if it takes 2 weeks to cable it up, how long am I going to take to configure it and figure out what's wrong? So that's exactly the value that we are providing. This cluster I can bring up from scratch within 8 hours now. That includes OS deployment time, compiling the libraries, which probably take 2 to 3 hours, and setting up the day two ops. And all that is available to our customers as part of this validated solution. Now, moving on, again, because I want to keep focus on those network engineers, the point is that this is how a rough image of the training server. Different vendors have different designs. For network engineering point of view, more or less, they are same. These servers have some dedicated ports for inter-GPU connectivity. These servers also have ports for front-end network and for storage connectivity. Now, when a training is running, and if let's say I only need 8 GPUs to run that training, the traffic among the GPUs is not leaving the server. Internal inter-GPU communication happens via something, whatever is the vendor is designing. AMD has something called Infinity Fabric. Intel uses direct point-to-point Ethernet links. NVIDIA has an NV switch technology. But when training crosses the boundary of a single server, that traffic uses the inter-GPU link. So that essentially means we're going to talk about 4 networks, something that you were referring to a few minutes earlier, right? There would be an inter-GPU backend network. That network only talks about or communicates the traffic between the GPUs. Then there would be a front-end network. This is very similar to a typical data center LAN environment, right? Then there would be a storage network. This is where a shared parallel file system storage device would provide similar access to all these GPU servers that are running the same distributed job. And then, of course, there is a management network that provides out-of-band access to all these devices. Now, for most network engineers, the 3 networks that are shown below on this slide, they are nothing new. I think the new thing, a little bit new, not entirely new, a little bit new, is really the inter-GPU backend, right? So I'm going to focus on that. And when we talk about designing that network, the basic idea is it's a simple spine leaf design, something that almost every network engineer is very comfortable with 2 major differences. Number one, these networks, design them in a non-blocking, non-oversubscribed way. If I try to break it down, what it means, this design is based on a 64-port Cisco Nexus switch. On that 64-port switch, if 32 ports are connected to the host, 32 ports are going to the spine. That's simple logic, right? So no traffic or no host is being blocked from the network. That's why we call it as non-blocking design. There are people who use different names, maybe 1:1 oversubscription, no oversubscription. The point is that. The other different piece is that how exactly the hosts connect to the leaf switches of this network. So if you look at this design and look at host 1, the first port connects to leaf 1, second port connects to leaf 2, third port connects to leaf 3, and so on. And if there are 8 ports, we use 8 leaves. Then the second host is connected in the same way. In other words, if I have multiple hosts, the first port of all the hosts goes to leaf 1, second port of all the hosts goes to leaf 2, and so on. This is called a Rails optimized design. Now, Intel follows a similar approach, not the same approach, a similar approach. Now, before talking to Intel, I wanted to highlight that how would this scale, right? So to connect 32 hosts, and assuming there are 8 GPUs within a host, that would lead to 256 GPUs within a cluster. And by the way, as I said, I'm keeping the focus on an enterprise environment. This probably, again, to a question, may not fit to a hyperscaler environment. But for an enterprise environment, if somebody wants to deploy a 256 GPU cluster, which in my view is a huge amount of compute power. So for that, somebody would use 8 leaf switches and 4 spine switches. And if they want to scale it even further, let's say to 5 and 2 GPUs or maybe 1,000 GPUs, have similar scalable units, connect the leaf switch of one to the spine of other, and vice versa, in a non-blocking design. That's the key, right? Now, I was referring to Intel a few minutes earlier. As I said, Intel follows a similar design. They call it as plies. They don't really use the word Rails. The idea is similar. In Intel, this is a Gaudi 2-based server design. It's very similar to their Gaudi 3-based systems. Essentially, the first port on the server connects to ply 1. Second port connects to ply 2. Third port connects to ply 3. And then they don't go more than 3 plies. What they do, fourth port again connects to ply 1. Fifth goes to ply 2. And sixth go to ply 3. And then every server repeats that concept. Now, difference here is that, notice there are no spine switches here. These are 3 independent and separate networks. So how would we scale it up? I can have 116 hosts to provide 128 accelerators within a single subcluster with no spine switches here. However, I can have more such subclusters to create a larger cluster and just keep on adding spine switches to it in a non-blocking fashion, right? Now, again, for network engineers, think about what kind of challenges it would create, right? Because typically, data center design is based on top of the rack switching architecture. There are probably 24 or 36 servers in a rack. This number varies all the time, but there would be cables, hopefully copper cables, which are not that expensive, connecting from these servers, every server in the rack going to the top of the rack switch. The top of the rack switch will connect to probably middle of the row or end of the row switching architecture, right? All that model changes following this design, because imagine earlier when I was taking the example of NVIDIA's design, and if I have 32 servers, I want to connect every server to every switch. So even if I put 32 servers in a row, imagine I have to find longer cables to run from one end of the first rack to somewhere probably 28th rack or 29th rack. And then every server must be capable of doing that. Now, if I divide that 32 servers not in a single row, but multiple rows, then it's a kind of a new design, if I can call a middle of a row. I would have to probably use the word middle twice, if that even makes sense, but something like that, right? So I think that's really relevant for network engineers, because, a lot of us probably may not go to that level, but for those of us who go, realize probably cabling and these kind of things cause a lot of delay. As I said, in my own cluster that I operate, cabling would take probably 2 weeks. After that provisioning, we can do it 8 hours.
I'm no network expert, but let me state that at the outset. Why is it that the Intel doesn't require a spine switch, whereas the NVIDIA does in the smaller configurations?
So it depends on, I'm going to talk about that briefly. It depends on how the collective communication works and how exactly they build their topology map for inter-GPU communication. The answer lies in that, right? Now, there are some architectures where it's potentially possible to eliminate those spine switches even in NVIDIA's Rails optimized design, right? But remember, I used the word potentially possible.
Wishy-washy.
Yes, there are softer knobs and there are some exceptions. That's why they don't remove it. But if all goes well, traffic will not go to spines even in NVIDIA's Rails optimized design. Now, trying to explain that a bit further, whatever I just explained, 2 big questions arise. The first one is, why? Why are we connecting like this? Why can't we just do top of the rack? Now, by the way, if you just do top of the rack design, where all the ports of a server just goes to top of the rack switch, that's okay. It's not a showstopper. Things will still work. But the question?
It would work slower, right?
It would work slower, right? And that's what I'm trying to understand. And for this explanation, probably take a step back, and if you know this thing really well, you'll figure it out that I'm taking a lot of assumptions here just to simplify it for a network engineer. And think about if, let's say, I have to add 40 numbers, right? So I can have probably 4 GPUs. And I'm taking the example of 40. In reality, this would be 4 billion, 4 trillion. Then I can divide this 40 numbers into 4 sets. Use 4 GPUs, pass on those 10 numbers to each GPU. So each GPU adds those numbers and then come up with one result, right? This is a basic distributed parallel processing, right? At that point, all these GPUs have to sync their states with each other so that they have the unified sum, as well as when they are ready to calculate the next set of 40 numbers, they know what to add it to, right? So for that, they would have to do something called a collective communication, right? All of them have to talk to each other. That's why it's called collective communication. There are many ways of doing it. Things like all reduce scatter, all gather, send receive. Without going into that detail, the point is that how can they really talk to each other? One approach is all the other GPUs send their calculated sums to one GPU. That one GPU again adds these 4 numbers, send the answer or the value back to all the GPUs. So every GPU has the same information. And you could probably guess not the best approach here, right? Because first of all, GPU 1 will get overloaded here. The second thing is GPU 1 is working to add these numbers. The rest of the 3 GPUs are doing what? Nothing. So, in this particular example, not the best approach. The other approach that I can do, and by the way, there are a lot of algorithms in this area. One approach that I can do, I can probably create a ring. Maybe we can create a ring among all of us. And I can pass on the information to you. And exactly at the same time, you pass on your information to next, and next, and next. So none of us are sitting idle at the time. And then I do the same thing again and same thing again. Between 4 GPUs, if I do it 3 times, every GPU will know what the previous GPU has and the previous GPU has and the n-1 GPU has. So essentially, every GPU learns about the state of every other GPU within a cluster by using 3 iterations within a 4 GPU cluster. Right? Now, how would this translate to a network design? Now, if you go back to that 8 GPU cluster design that I was referring to earlier, if there's a distributed job running within the server only using 8 GPUs, there would be a ring created internally using one of their, whatever the internal mechanism is. As I said, in AMD Infinity, Fabric, Intel direct point-to-point links, NVIDIA NV switch. If there's another server or another host, it would have a similar ring. This ring that you see right now on the screen has a root on GPU 1. But if I'm running a job between 2 servers that needs 16 GPUs, I would have to, join these rings somehow. So I can join them in a simple way. But there won't be just one ring because there are 8 GPUs. So essentially, there would be like, every GPU may have its own collective communication going on at the same time. So another GPU will create a ring, and all the GPUs will create the ring, and they would have to be joined. Guess what? That's why we create a Rails-based design so that all these rings can be allowed to communicate using a single hop forwarding. And this is why it explains a Rails-based design or Intel's Fly-based design. Similar concepts, but different way of cabling. It just depends on how they are creating the inter-GPU topology to talk to each other. Minor enhancements that every vendor will keep on doing as to provide that minor improvements every time. The next question is, so for very relevant for network engineers again, so what exactly is flowing on the wire at that time? Right? Collective communication is happening, but what exactly is flowing on the wire? Now, again, I'll go back to my simple example of 4 GPUs. Now, imagine if these 4 GPUs are within 4 different servers. These 4 different servers will actually talk to each other via network switch, right? There would be cable connecting to a network port. So if I take a sniffer on the wire and try to figure out what exactly is flowing, remember, although there's a collective communication going on, it really boils down to the point-to-point communication by directly accessing the memory of another GPU. If it's in a single host, it's a direct memory access. If there are 2 different hosts, it's remote direct memory access. And the way we achieve remote direct memory access over Ethernet fabric is simple RDMA operations. How exactly RDMA operations are carried? Essentially, the same networking logic. We take the buffer, whatever the amount of data we want to exchange, break it down to the maximum packet size, attach headers to it. In this case, it would be UDP IP traffic and forward it to its destination using the standard forwarding function of the network. Now, for all the network engineers out there, how many of them are super comfortable in handling UDP IP traffic? All of them? No big deal. It's a flat L2 network or flat L3 network. This network doesn't require those kind of complex policies or advanced segmentation approaches that we typically see in a data center network, because this is an inter-GPU dedicated network. And all it's doing is UDP IP traffic. Now, a few things that I want to highlight, which in my view, I see a lot of confusion around. When we talk about a protocol, typically in networking world, when we talk about, let's say, TCP runs probably internet, right? When we talk about TCP, there's a header for TCP, right? So people expect, when they look in the wire, they expect a header. When people talk about UDP, they expect a header. When we talk about Rocky V2, guess what? Where's the header? There's no header, by the way. That's number one. Not just Rocky V2 doesn't have a header, even there's no such thing as an RDMA header here on the wire. The header is really the InfiniBand. These are InfiniBand verbs, like the verbs, which are transporting the data between the memory of 2 GPUs. That's where it really boils down to. For network engineers, as I keep on saying, it essentially boils down to UDP IP traffic. So it's really simple, but some additional challenges, which you kind of like, talked about earlier. There are some additional challenges. So what are these additional challenges? Number one, packet loss. Now, remember, it's UDP here. So unlike TCP, in a typical data center network, there's would be a lot of TCP traffic. If a single packet is lost, TCP is capable of detecting and retransmitting that packet. UDP does not have that capability. So what would happen if a packet is dropped? Remember, in the previous screen, I showed you RDMA operation. If a single packet is dropped, what would happen? Either the entire RDMA operation has to be reinitiated, or all the packets since the lost packet have to be resent. Whatever you do, it's going to delay your entire RDMA operation and the collective communication. So we want to avoid that. And the way we can avoid that is using priority-based flow control that can be used to create what we call as a lossless network. Now, one thing I want to highlight, when people say lossless network, it causes confusion sometimes. And I know it's all written, but still, because of the naming, when there's a lossless network, there's no guarantee that packet won't be lost.
Good marketing,
It's
right?
less loss network.
Yeah, it's just like there's never a guarantee, by the way, right? If like I'll talk about CRC, if the packet is corrupted, it will eventually get dropped. I mean, yes, we can use forward error correction to recover, but FEC, forward error correction has a very small threshold. If the bits are corrupted after that, there's no way packet will be automatically reconstructed on the receiver, right? So that's really key point, and like it again boils down to the same key importance of day 2 ops crossed as day 0 ops, which are really important for all infrastructure engineers, that when machine learning engineers like Nicholas blame, hey, why my training job is not running, and I'm seeing a lot of out of sequence packet, which is like a RDMA layer counter, which is being caused by CRCs, you got to find that, right? So all these capabilities are inbuilt in Cisco products. In fact, Cisco Nexus dashboard can automatically detect any CRC as and create an anomaly. That itself saves hours of time for somebody who's trying to find where the problem is.
Who or what is detecting the lost packet? So that UDP cannot detect the lost packet.
Well, as a protocol, I keep my focus on UDP as a protocol.
I understand,
Well, but
so where is it? Where is the lost packet being?
there would have to be a timeout of some sort at basically whatever the job is running, saying.
So it's already at the operating system level.
Well, it's either at the operating system level or at the application level that's doing this. Whatever is doing these operations, at some point it's going to say, I can't complete this operation because I never got my next piece of information. So
Yeah,
but I mean that was one of the things that TCP was designed to attempt to prevent. And I mean TCP has its own downsides, but it typically has a faster recovery time than coming up with your own home cooked way of recovering from a UDP loss.
and when you say home cooked, depends what home and who's the chef. So
Well,
right. So there are folks who are able to improve TCP, but again, I want to address the enterprise market and the network engineers who work in those enterprises. I don't think all the research and development happens in those markets or
Okay.
in enterprises. Enterprises are focused on delivering value to the customers.
Since you were bringing this up and starting to talk about this, I was going to ask: Are you involved in the Ultra Ethernet consortium?
I'll talk about that. Yes. So yeah, Cisco is a founding member and the steering member of the committee. Yes. So I'll briefly mention that in the end, right?
Okay.
But that's something happening in the future. I think today, when customers are deploying and like network engineers,
It's happening now, but the results will be available in the future. Yes. Okay.
Yeah. Right. So talking about the next challenge, and that like really aligns with the next question, is what happens when the packet is lost. Essentially there would be timeout kicks in and there would be delay. Now look, network delay is not a surprising factor. Of course, whenever you send something via a network, it's going to cause some delay. It's a speed of light that's governing factor. For every meter of cable length, it's going to cause a 5 nanosecond of delay. Speed of the network interface, like how fast you can put bits on the wire, right? So for roughly, I think NVIDIA uses 4K size frames for doing those RDMA operations. So when you see the UDP IP packet, it's roughly around 4K. If I want to send 4K size packet on a 400 gig link, it's roughly 80 nanoseconds. So that delay, I don't think as a network engineer, I can avoid that. That's fixed. What really varies here is the queuing delay, like how long a packet is sitting within the queue of a switch, waiting for the packets ahead of this packet to be transmitted. And that varies heavily, right? So all the focus is in that direction. And some of the features that we have on our switches is like, how do we prioritize that last packet in the operation, which is the ACK packet or response packet, so that already initiated RDMA operations complete faster and not really waiting behind some large size data packets. So that kind of QoS rich feature sets are available on the Cisco switching product line already today.
And the QoS and these things have been around for a while in other applications, but in this instance, what you're referring to specifically is in this context, in this networking scenario for this type of an application, this workload of machine learning AI. Is there anything specifically that you're doing that's different in QoS or your flow control as compared to other applications that you've approached before?
Well, the basic technology is same.
Okay.
How do you apply it really makes a difference, right? How do you test it for months and like figure out this minor change in my QoS setting actually leads to, let's say, 5%, 10%. If you change something on the network and it leads to 5% improvement, I think it's huge. It's you're not even touching the end devices, by the way. Most of this is done within the end devices, right? Like it's done on the NICs or the GPU, right? So hopefully, I mean, you guys have been around long. When we talk about
train of code that had to be created for what you're describing, these were investments that were made for applications generally speaking. This just happens to be one particular application. This just happens to be how it might be useful in this application context.
Special purpose network for GPU, if you will.
Yeah.
I'll talk about one specific enhancement that we did, but your point is totally valid. That's what I'm trying to convey, that guys, this is one application for a network.
Which is
how different it can be.
I thought that's where you were going. I just wanted to double check that. So essentially you're saying that you can buy HyperFlex Fabric equipment and do all of your networking, including this new type of workload, which is GPUs. Maybe there's some tuning that you need to do around cabling or specific configuration, but it's largely the same. So if you're an enterprise, you can use the same sort of equipment you're already familiar with, or a lot of the techniques are the same. You don't have to go out and buy a completely dedicated, separate piece of stuff with exotic, weird things that needs to be operated by a completely different team. Is that accurate?
Well, yes and no. Look, the kind of traffic requirement that you have in these backend clusters, these are like you got to dedicate every resource. With that requirement, you can connect additional cable to the same network, or if it was me, I would build a new fabric altogether. The reason is I don't want to create any conflicts and like end up troubleshooting all these issues, which Nick would say more not.
Is it these are the same SKUs that we
same SKUs but dedicated different duplicates of them.
Yeah, kind of. I mean, part of it is also like enterprises
fabric.
already know Cisco quite well. So if I'm going, I want to build a GPU cluster, I have a choice to say, well, I can go with the thing I already know and have some familiarity with, or I can just go, you know what, completely new workload. Who cares about what I used to do? I'm going to build a brand new thing with all new stuff and completely new vendors and ignore you totally. That's probably not what Cisco
like
wants,
that.
but
if you ignore me.
Yeah. So I'm trying to understand how much of what I already know and understand is relevant in this new context, and how much of it is, if I wanted to do this, should I train existing people to know a few new things and maybe hire some people and operate some stuff and build some infrastructure which is just like it, or do I start completely from fresh? And I'm thinking back from when we were doing storage many, many years ago. It was like, well, we'd have a completely different protocol. It'd be fiber channel switches, and it was different gear run by someone completely different. And then we went, you know what? We can run storage over IP. Let's just use Ethernet, and yeah, we'll have a storage network and we'll have front end networks, but everything else is basically the same. Can we do that with GPUs?
Who would have done something like that?
Madness. Just it was
you
insane.
haven't mentioned MDS or DCNM Prime or other parts of the Cisco portfolio.
You don't want me to mention that.
I'm just saying. You haven't mentioned any of that. I had to mention that, right? so this is an entirely Ethernet proposition that you've outlined. Yeah. So there is a purity, if you will, in the design that we are talking about right now. Yeah. It's a very short list of things. So we talked about the bill of materials earlier. And so the bill of materials, there's no exotic SKUs that I've heard.
Speed, higher speed.
Well,
Yeah.
but is it exotic?
400 versus 100 gig. Is that exotic?
So we see GPUs already today able to send and receive 400 gig all the time. All of them are doing that exactly at the same time. That's why earlier I said I want a non-blocking 1:1 oversubscribed network. And honestly, until I ran this and saw this, I like that exactly when the moment of realization. Okay, yeah, that's real. So,
but conversely, you can take the 400 gig this networking equipment and bring it right back into the data center. Maybe your data center is running at 100 gig, or isn't using all 400 gig bandwidth on each link, but it's still effectively the same Cisco gear, right?
yes. So, well, that's exactly what we're saying today. Yeah, so you see some of my designs are based on that 9364D GX2A switch. Yeah. It's not a new switch.
Not a new switch.
Right, not a new switch. It's not like I'm going to build some magic Ethernet switch for this use case. But yes, we are building some features based on that, right? So that's something I'm going to talk, right? Now, when we talk about all the GPUs sending and receiving traffic almost at the same time, of course, network congestion, the basic problem that happens.
I want to.
Sure.
I think this will lead into that, but I want to go back one slide to something you had on the previous in network delay, and you say at the bottom, detecting anomalies at a per flow level, and at the AI and the inter GPU communication, what is a flow?
For network, today it's layer 4, a UDP flow, which is source IP, destination IP, UDP, and like the source port and destination port.
Okay. So, but from an AI perspective, we're talking about one GPU communicating its results maybe to the next GPU. That link is also a flow. That's what you're looking at.
Yeah.
Yes.
So, I mean, flow is a generic term. You decide how you want to define it. But again, for network perspective, that's what matters, because I do not believe a typical network engineer would go and like operate where a machine learning engineer would operate, right?
Right.
Okay, I've been signaled to keep moving. Okay, so when we talk about network now, there are many approaches to deal with network congestion. Depends on the cause of the network. There's one cause where the end devices are slow, not really slow, but they're stuck. And because if we use priority-based flow control, we create a lossless network. One of the kind of like specific phenomenon that happen in lossless network is that when there's a congestion, it spreads to the source of traffic, right? And that affects many other devices in the fabric. So to deal with that stuck end device, we have the capability to automatically de-isolate that stuck device from the network, and also automatically, actually I said it the other way, isolate the stuck device and then de-isolate the same device when it's doing well. That feature is called as PFC watchdog. In addition to that, there's something called a DC QCN, which is based on a paper that came many years earlier, which is again based on the original ECN RFC. The way it works, the network detects congestion, informs the end devices, the end device reduces the rate. The kind of support it needs from the network is that the network should be able to mark that ECN header or the field in the IP header. And when the congestion notification packet is being sent by the destination to the source of the traffic, probably prioritize it to them.
For the storage people here, ECN is known as DCB for most storage people.
Storage people, like you're saying, Fiber Channel?
Oh, well, no.
Ethernet, iSCSI.
Ethernet, iSCSI.
Yeah,
but it's
ECN. That's exactly, you're right.
Yeah, but it's everybody except Cisco calls it data center bridging.
Okay, let's move on. So that is one way of controlling congestion. However, there are other ways of handling congestion, which is totally based on the end device based mechanisms. And these end devices, because these are GPUs, extremely powerful GPUs, they are able to measure the real time round trip times of these operations. And based on that, able to control their rates wherever congestion is seen per flow, right? For this, the way switches help is prioritizing those ACK packets, again, what I mentioned a few minutes earlier. Because if we do that, we can actually having a consistent RTT values on the end devices. And also, again, especially with DCQCN, look, I do not believe somebody will get it right the first time. There's like heavy amount of tuning needed for that. So how do you figure that out? Nexus dashboard actually monitors all these things, provides what exactly is happening, and then also applies a configuration consistently across the network. Now, moving on, one of the major causes of congestion, which kind of skipped on the previous slide, is the non-uniform utilization of the link. Now, really, the non-uniform utilization of the link is not really a problem because that happens all the time in a typical data center network. The problem is with the inter-GPU network, all links are sending and receiving at the same time. So even if there's a minor imbalance, let's say I get 800 gig of traffic, I want to send it on two 400 gig links. If one link sends at 98%, the other link is expected to send at 102%, which is not a thing. So of course, it's going to cause congestion and cause problems, right? Now, there are a couple of enhancements in this. And by the way, these names you'll see across the industry, but implementation differs based on the silicon that we have. So one is like dynamic load balancing. The way it works, it looks for the real-time rate of the interface. And also it detects the inter-packet gap, assuming every RDMA operation has some gap within it, and then moves the other RDMA operation to the next link. So you have the results on the left. You see the default ECMP approach with 256 GPUs running an all-reduced collective, and compare it to the graph on the right. Right? So this is the benefit. The other mechanism is we can increase the number of flows flowing through the network. Now, again, as I said a few minutes earlier, you decide how you identify a flow. So instead of going a layer 4 UDP flow, actually we can identify a flow based on every InfiniBand destination queue pair and then send traffic to each of these queues on a separate link. That significantly improves your uniform utilization of the link. Another enhancement in that direction is like static pinning. Now, remember, as I said, these are non-oversubscribed 1:1 network. So for every 400 gig link going down to the GPU, I have a 400 gig link going to the spine. So why not I just like put all the traffic and directly pin that this traffic goes on that link, this traffic goes on a separate link, and so on. That would make the traffic extremely deterministic and would avoid those issues of ECMP load balance. And this is one of the points that I was referred earlier, is that not just the throughput problem or throughput challenges there with these inter-GPU network. The other big thing is all these GPUs are sending and receiving at the same time. So not just throughput, now we're also talking about large burst all the time, everywhere. So one of the things that we did on our switch is that we were experimenting different ways, and we have always supported a shared buffering architecture. And we said that if there's an elephant flow coming, which is a large throughput flow coming on a port, allow it to consume more buffers and take some space from the a shared buffer space. Worked well all the time on typical data center networks, as well as the storage networks. But because of the traffic pattern of inter-GPU communication, as I said, all these ports are seeing the burst at the same time. So why don't we just dedicate buffer to all of them? Because all of them need it exactly the same time. We did that, and we saw up to 17% improvement.
What was the strong function that gave you the up to 17% improvement? What was the differentiator between no improvement and 17%?
So this is based on the reduced scatter collective. You see the bottom graph. I'm taking the best number. Of course, I should, right? But I have the rest of the numbers. Your mileage will vary because, of course, the kind of data set you use, the kind of algorithm you run, there would be different buffer size that would be transferred, and then look for where you fall and like use that. Don't even listen to me, run it by yourself. That's what people should do, right? But be aware, because we experimented, we found better results, consistently better results, we decided to productize. Okay, now talking about the question on UEC, right? Now, of course, what is UEC? It's Ethernet-based AI/ML infrastructure, trying to scale it up better and provide better performance out of it, right? Now, Cisco is a founding member, also a steering member. The key point is that there are no changes needed at layer 1 and layer 2 of the OSI stack. However, as a baseline requirement, there are a few things needed, something like a priority-based flow control, ability to mark ECN fields in the IP header, ability to have multiple traffic classes on the network switches. We do all of that today. I spoke about that. Right? In fact, most vendors do that today. Right? And because it's Cisco Silicon One architecture, which is programmable, which is kind of future-proof. Okay. Now, in the interest of time, what I want to do next, I want to invite Nicholas, who's a machine learning engineer, and he's going to share his experience how he built a generative AI application using the infrastructure that I.
Awesome. Hello, everyone. My name's Nick. I'm a software engineer here at Cisco, focusing on developing AI ML applications. So I'm a part of the data center networking group. My team developed iNAM, which stands for Intelligent Networking Automation and Management. It is a model that is embedded directly within the Nexus dashboard platform and will be able to provide overall observability and insight generation into what is going on within your network, and hopefully be able to provide accurate anomaly detection and remediation techniques for how to do that. A little bit about me. I studied mathematics and statistics in college and was a part of various AI research labs during my time there at UCLA Health and at Cedars-Sinai. Now, my talk today mainly focuses on how I leveraged Paresh's infrastructure that I just went over to develop this application itself. So I'll go into a little bit of why I needed this on-prem AI ML infrastructure. So initially, basically what is happening is we have this.
This runs in the switch, or this runs in the cloud, Hyperfabric cloud?
So this would be running on your customer deployment within your UCS server, or anything that leverages CPU-based deployments. So we're actually doing inference on the CPU. That is one unique thing that I'll get into later. So for how this worked on an on-prem AI ML infrastructure, why I needed it. So at Cisco, we have a huge data collection of all this relevant information regarding networking best practices, attack cases, how to resolve issues, and we're not able to just move this to the public cloud, right? So we need to keep this on-prem. It's also extremely expensive if you want to go start renting GPUs. For example, just renting 8 or 1 GPU for an hour, it's quite expensive, as I'm sure you probably know. And you're also limited in the amount of memory per each GPU instance you can rent. So say each one of your GPUs has 40 to 80 gigs of VRAM. This limits the amount of data you can put into your batch size. And of course, the amount of data you can shove into each GPU determines how fast your training runs will go. The overall flops will remain the same. However, the amount of times the models actually have to consistently sync up, there's a gradient descent, changes. So it leads to overall efficiencies in the speed up. So after being able to leverage Paresh's on-prem infrastructure, it allowed us to train on this internal private knowledge base. And so our training runs, which would typically take around 2 days to 3 days, were now going in the order of hours. So we were getting training runs in the order of 6 to 8 hours about. And this is leveraging distributed data parallel training, where you're taking all your data, think on the order of 500 million rows, sharding it across, and each GPU gets its own distinct section of this data, and then we run these processes in parallel. And so, as you can see, we've processed over 5 billion tokens in under 6 hours, which is quite impressive, considering that this run, using the cloud infrastructure we were using before, would have been scheduled to take over a month, which is obviously not great when you're trying to test out and see whether or not your fine-tune is actually going to be good. And then, so we're leveraging, a really cool thing about having this infrastructure as well was that it allowed us to leverage the shared memory across all of the GPU clusters, RAM and VRAM. And this allowed us to load all these different fine-tuned models into memory and perform what was called model merge. This led to a novel development from our team called QLoRa Blend, where you're basically taking a bunch of different fine-tunes of different models, each their own expert. You can think of one being a Q&A expert, one of them being an expert on your target domain, which is like networking, one of them being an expert at just chat applications. And you can fine-tune these how you will, and then you're performing, using some linear algebra magic, a merge, which condenses all of these models using what is essentially a high-dimensional vector space, condensing them down into one unique model, which we then called iNAM. Overall, what we ended up doing was we took an existing open source foundational model called Phi3, produced by Microsoft, and did additional fine-tunes on our own domain set to produce what we call iNAM. And so this is what you would think as Cisco internal public-facing documentation, public APIs, as well as our own internal knowledge set, which includes all these years of attack cases, best practices, and that kind of general networking knowledge. We also heavily rely on various forms of RAG to give long context understanding, as LLMs are great at doing knowledge synthesis. So what you can think about is we're using this networking knowledge that we have entrained during fine-tuning, as well as combining the knowledge that we can give it during inference time. And so the way this gets engineered is fairly standard compared to your web applications that you would expect. You would expect a backend API that does all the query routing. This is where most of the complex logic is. to actually develop the RAG system. So you'd be doing identifying user intent. And I'm sure you're going to hear a ton about different ways people are doing RAG, whether it's traditional with a vector DB, graph where you're building out knowledge hierarchies and then figuring out what entity relates to another one, or even just multi-agentic approaches where the LLMs themselves are coming up with unique ways of doing this. And so we leverage a little bit of all of these in our approach as well. So we developed this application to be running directly on the CPU itself. And this is quite unique. So most LLMs, as I'm sure you can leverage the CUDA cores within GPUs to parallelize their operations during inference time. For us, we want to keep the data sensitive because customer deployment has sensitive data that they don't want to have leave their network. However, you can't really ask interesting questions such as, what is going on with my network? Or how can I go about fixing it if you can't have access to this data, right? You can't be grounded in the truth. You don't want it just spitting off hallucinations out of nowhere, right? So that's why the importance of being able to have this on the deployment itself is quite cool and innovative. So you have to be able to do this inferencing, which requires some low-level optimizations at the SIMD level, as well as various CPU suppliers such as x86, where you can do AMX and AVX instruction sets as well. So with all that said, I rushed through that a little bit, but we're going to go show a quick demo of how this all works. So now what you're seeing here is the iNAM application. What's happening here is it's synced up with Nexus dashboard, and Nexus dashboard is configured to monitor. It's configured to monitor one of the networks we actually use during training. So this is a bit of a circular moment here, where the network that Paresh set up, we trained on, and is now going to monitor and configure and hopefully absolve some issues with that very same network. So that's kind of cool in that sense. So we're going to go ask it a question, just to give some context, is to provide us some ideas about this inner GPU fabric cluster. So this is the name of the fabric that is we use during training, right? So this is the Intel 3-ply design that comes back. As you can see, we come back with some relevant context, and then our LLM will proceed with an answer. And again, this is all running on the CPU. And if you can see, it's still quite fast. The really nice thing is it's pointing out the fact that it's using Cisco switches and that it would be great for doing AI ML workloads. I'll give a second to pause here. As you can see, it's describing the design with the 400 gigs per switch with the leaf-spine architecture. And then we will go a little more into a question that we observed during training. So is there any traffic imbalance on the network? So we observed this that when we were running these distributed training runs across all the HPC nodes, we would frequently observe that 2 of the Ethernet ports would either be above or below the normal average rate. So if you were expecting most of these ports were operating within a certain range, 2 of them would be abnormal in that sense. And the big problem is if any of these nodes ever go down, your whole training run is scratched. What you have to do is you have to revert back to your latest checkpoint, which could be hours or days behind in many cases, right? So we'll ask this question and see what comes back. And you'll see that it is able to accurately identify and absolve pretty much the fact that there is a minor imbalance within the network. It can point out the 2 specific interfaces, Ethernet 130 and Ethernet 125, I believe, which has peak and below the average rate between the other interfaces.
Can you ask it how many giraffes there are on the network?
That's a great question. Sadly, we can't because this is recorded.
Oh, that's recorded.
Many giraffes.
But and then we can go from here and we start asking further questions and drill down how can we go about fixing these issues, right? So this is the really cool thing about this. And it will come back with some general ideas of how you can go about analyzing these patterns, setting up ECMP load balancing, and as well as continuously monitoring and going about your network. We could go in further and we can even provide CLI commands for network engineers if they're more about that, or if they want to go via the UI of Nexus dashboard themselves, we can use the public-facing documentation as context for the RAG to be able to come up with these great responses. So with that, I'm going to conclude the demo. I know we're running short on time, and I'm going to hand it back to Paresh so we can go over some concluding steps over how this is all
I
working.
had one question.
EMP under the bus too. That was nice.
Yes, it did go easy.
Yeah, one question. Was the fine-tuning just a way to compress the data so you could then run it on the smaller smaller places?
Yes, so the fine-tuning was mainly, so we took a base foundational model, right? This is generalized across all internet. So it's kind of like a general purpose. It can do anything. We want it specifically targeted for our use case, which is doing network analysis of a configured fabric, right? And so that was the main purpose of that, as well as to get it outputting responses that we find to be better, right? So this would be adding in reinforcement learning with human feedback, certain answers and responses that we think would be better appropriated for a specific design such as this chat application.
Right.
That's kind of the main idea.
But many times you could still use RAG for a lot of that. It's not like
You can. So we actually fine-tune it specifically for the case of being able to do long context synthesis, where you are fed huge chunks of data and have to figure out what the actual response would be.
So the fine-tuning was about preserving context.
Yeah, so most of our, so within each row of data, you can say, would be multiple paragraphs with the data during the fine-tuning phase. And that was one of the big insights, because if you just train it on basic Q&A and are getting one-word responses in the answer, well, shoot, that's not going to help anything, right? You're going to get a one-word response when you output this model. And no one wants that. So that was one of the key insights.
The other thing is that you're gathering data from the Nexus dashboard.
Yes.
As well as trying to understand it and analyzing it and such. So, was that part of the fine tuning, or is that part of your agent generation?
So that's part of the RAG, is being able to feed it the context from the customer deployment at runtime. You're able to inject the context from that.
Part of the RAG, is that what you said? So it's part of the vector database. So you're doing a vector query against the dashboard data log to try to understand what to do?
Kinda. So you're right that it's using a vector database, but the way it's using it is a little different than what you're describing. In the shortest explanation of how this works, we're identifying the user intent via a prompt query. From there, using an agent to figure out where this would best be routed via function calling, to then come back with the correct context that would be used to supply this. So we have defined certain functions that this LLM can go out, reach out, and use, and then it will come back with the correct data, which we know with a certain degree of accuracy will be right every time.
Like the disposition codes for attack or something like that.
Yeah, exactly.
Yeah.
Hopefully it's conveying the point, the value of having an on-prem infrastructure, because without that, Nicholas could not have trained his model based on years worth of the stack information, right? So this is the same model that most enterprises will go through. Now, a lot of these network engineers in those enterprises, as I said, it's simple UDP IP traffic, so quite simple from that perspective. Most of the challenges can be avoided with a well-designed network, maybe Rails-based or Ply-based. And of course, there would be some exceptions. For that, there are use cases or features built like dynamic load balancing or ability to load balance based on the InfiniBand destination queue pairs. And the last point in that, that's the entire purpose, that we wanted to bring a first-hand experience of me as an infrastructure person who actually qualified these systems, and Nicholas, who built this application by himself, to convey the point that we are qualifying these systems for our customers so that customers can confidently deploy.